Hi everyone, the lab for today will be over solutions and solubility. This will be another wet lab, so it's one you actually have to get your kit out to do. And I wanted to take a little bit of time to go over the intro with you and just to talk about some of the main concepts. So firstly, the materials you'll need, your safety glasses, test tubes, metal spatula, which is your scooper essentially, transfer pipettes, and a glass stirring rod. If you, for some reason, don't have a glass stirring rod, any other thin object that will fit into the test tubes will be just fine. So something like maybe a popsicle stick or something like that if you have one handy. Okay, so those are the things that come with your kit. But the things that won't be in your kit are your cell phone, and this is just to record yourself. You'll need salt, so just table salt is fine. Sugar, table sugar, that's all you need. Vegetable oil. If you don't have vegetable oil, you could also use olive oil or sesame oil, something like that, some kind of cooking oil. Anything like that would be fine. Peanut oil would be fine too. Any kind of oil should work just fine. Isopropyl alcohol, so this is your normal bathroom alcohol, which should say something like rubbing alcohol. A Sharpie, or some other type of permanent marker. Okay, so the main purpose of this lab is to identify polar and nonpolar solvents and solutes. Okay, so the main two things we're going to be talking about here are mixtures and solutions. And now mixtures come in two flavors. So a mixture is just something that contains two or more substances that are not chemically combined. So it's a mixture of one or two or more things. So it could be a mixture of gases, it could be a mixture of liquids, a mixture of solids. You could have a mixture of a solid and a liquid, etc. And these come in two different flavors, as I said. So basically homogeneous and heterogeneous. So heterogeneous just means that they're in different phases. Okay, so that would be something like if you put sand into water, like at the beach, for instance. You can definitely tell where the water ends and where the sand begins, or where the sand ends and where the water begins. In other words, if you were to take a glass of water and put a handful of sand into it and give it a stir, the first you would see the sand swirling throughout the water, but if you were to let it sit, it would settle out eventually. And you'd be able to say, okay, this is clearly the sand layer, and this is clearly the water layer. Now, in a homogeneous mixture, this is when there is no separation of the phases. So this would be they're in the same phase, such as the aqueous phase. So if I take something like honey and I dissolve it into water and I mix it in, the honey will dissolve, and I won't be able to determine the difference between the two, or something like salt or sugar, anything like that. Okay, anything where you can't distinguish between the two layers. So I can't point to and say, okay, this is where the salt begins, or this is where the sugar begins, and this is where the water begins. They're all just one big mixture. So this would be something like a glass of sweet tea, maybe. So you have the oils from the tea mixed in, or the tea leaves mixed in, and you have the sugar, maybe if you added sugar to it. And that's all mixed in together, and you can't tell the difference. Now, what we're going to particularly be talking about today is solutions. And there's two parts of a solution. So one part is the solute, so S-O-L-U-T-E, and then we have the solvent. Okay, so solute and solvent, similar words, but they're two different components of a solution. So the solvent, this is generally speaking what we have more of. And generally it's whatever the solution takes the phase of. So if it's, for instance, an aqueous solution, takes on the phase of the water, a liquid water. Okay, so that's going to be our solvent. The solute is generally what you have less of. So if you take salt and you dissolve it into water, the salt is going to be your solute, and the water will be your solvent. Okay, there's a few properties that go into making a solution from a solute and a solvent. And one thing that we need to know is that polar solutions dissolve polar solutes, nonpolar solvents dissolve nonpolar solutes. So if we kind of scroll down a little bit, we'll talk about polarity. Okay, so what exactly is polarity? So we have three kind of ideas here to think about. We have nonpolar covalent bonds, polar covalent compounds, and ionic compounds. So let's take a look at nonpolar covalent bonds first. So this is something like chlorine. It doesn't have to be chlorine, but this is a good example where we just have a diatomic element essentially. So two chlorine atoms bonded together. Now what's important about that? Well, what's important is that chlorine has the same electronegativity as another chlorine. So in other words, one will not steal electrons from the other. Okay, so this bond between the two chlorine atoms is completely balanced. So this could also be between two carbon atoms, two oxygen atoms, something like that, where you have equal electron sharing between both of the elements, or both of the atoms, I could say. Okay, so this would be nonpolar. Okay, so what about a polar covalent bond? Now, what's different here? Now, what's different here is how do you spot a polar covalent bond? Well, it's again a covalent bond, so it's sharing of electrons. But what makes it polar is that one element, or one atom, is more electronegative than the other. And what happens is that causes a slight negative charge on the more electronegative atom, so it's pulling those electrons away, and a slight positive charge on the less electronegative atom. Okay, so we end up with a covalent bond, so it's still sharing of electrons, but you can kind of think of it as being lopsided. So one of the elements is pulling, or one of the atoms is pulling the electrons away. And how do we spot an electronegative atom? So remember, your electronegative atoms are going to be further towards fluorine. Okay, so sort of up and right be where your electronegative atoms. So you think things like oxygen, fluorine, chlorine, bromine. Okay, those type of atoms, those are going to be your electronegative ones. Okay, and those are going to pull electron density. They're going to pull electrons away from the less electronegative atom. Okay, and if they're still bonded, so if it's still sharing electrons, that's covalent. Now, what about if I don't have sharing electrons anymore? What if I have an electronegative atom actually stealing electrons from the less electronegative atom? So something like a salt. So sodium chloride, for instance. This is just your table salt. Okay, so in this situation, the sodium, remember where sodium is on the periodic table, all the way over here on the left. Okay, so on our first column here. Okay, so sodium is actually going to give up its electron to chlorine, so that it becomes positive, and now chlorine, since it has one extra electron, becomes negative. And now since sodium has given up that electron, it becomes positive. Okay, so this would be an example of an ionic bond. Why an ionic bond? Because they're attracted to each other based on the fact that one's a positive ion and one's a negative ion. Okay, so here's some more examples. So here we have a polar covalent, such as in water. Okay, so oxygen, remember, is your electronegative atom, pulling the electron density away from the hydrogen. Okay, and you end up with a molecular structure, or a molecular shape, something like this. And this is mainly due to the repulsion of these lone pairs, but that's sort of not important right now. What is important is that you end up with a partially negative side of the molecule and a partially positive side of the molecule. And that's because essentially you have, again, a lopsided molecule where one side of the molecule is pulling all of the electrons away from the other side, and it ends up with what we call a dipole. Okay, and that dipole makes this a polar compound, or the fact that it is a polar compound gives it a dipole. You could look at that either way. Okay, so what about a polar covalent? Here we have, we have a carbon monoxide, so a carbon bonded to oxygen. Okay, so just within this bond, this would be a polar molecule. If that's all we had, is just the oxygen and the carbon, so the oxygen pulling electrons away from the carbon, if this is all we had, this would be polar covalent. But if we take a look at the actual molecule, we see that we have that essentially on both sides, so it's sort of counterbalancing each other. So in other words, we have equal pull in both directions, so what we end up with is nonpolar. Okay, so pay careful attention to that. So essentially what you're looking for is in a polar compound, you have a lopsided molecule. In a nonpolar compound, you have equal electron pulling in opposite directions. So they sort of balance each other out. That's sort of how to spot that. Now, when we're talking about solutions, we're going to be talking about intermolecular forces, and hopefully this is a review. Okay, so we have dispersion forces, dipole, and an ion dipole. And of course, we also have hydrogen bonding, but it's not listed here for this experiment. So dispersion, this is felt by all molecules and atoms. So if ever a question asks you what intermolecular forces are felt by these compounds, one of them should always be dispersion. And this is between all molecules and atoms. And this is caused by little tiny partial dipoles, okay, so instantaneous dipoles, what we call them, that are just caused by the actual movement of the electrons themselves. So essentially, if you can imagine an electron buzzing around this molecule, at the point it's on this side, that creates a partial negative, and the fact that it's not over on the right-hand side, that causes a partial positive. And if that gets close to another atom with a similar situation, these instantaneous dipoles will be attracted to each other. Okay, and while they're attracted to each other, that creates a force that pulls them together. And I didn't mention this, by the way, intermolecular forces. These are the forces that attract two molecules to each other, two atoms to each other it could be, or two molecules to each other. But it's between two different molecules or atoms. So that's dispersion forces. So this is in all atoms and molecules, and it's just caused by those instantaneous dipoles, which are just due to the movement of the electrons. Okay, then we have dipole and dipole. And just like what it sounds like, this is the attraction between two dipoles. And we're talking about permanent dipoles in this case. Okay, so this is for polar molecules. And as you see here, so we have an oxygen bound to a carbon bound to two hydrogens. And we know that the oxygen is electronegative. Remember that we found those up in this right-hand corner of the periodic table. Okay, so we know that it's going to create a partial negative. And if I have the same molecule next to it, that's going to have a partial positive and a partial negative as well. And those two dipoles will be attracted to each other, just like the two poles of a magnet would be attracted to each other. Okay, so it's the exact same idea here. Negatives attract positives, positives attract negatives. It's exactly the same idea here. And this is for polar molecules, and this is called dipole-dipole. Now, we also have hydrogen bonding, which is kind of a special type of dipole-dipole, but not particularly necessary for this lab, I don't believe. Okay, so the last one, we have ion dipole. And this is, again, exactly what it sounds like. So if I have an ion and I have a dipole, well, I can have ion-dipole interaction. So here we have water, which again has an oxygen pulling electron density away from the hydrogens, giving it a partial negative. And here I have a positive ion. So this could be something like sodium, for instance. Okay, so the negative part of the oxygen, or negative part of water, will be attracted to the positive part of our ion. Okay, so how do we know if something will dissolve or not? Okay, so solubility, this is what we're talking about really when we're talking about solutions, and we're saying, will something dissolve? Again, we're going to go with like dissolves like. So if I have a polar solvent, it's likely to dissolve a polar solute. If I have a nonpolar solvent, it's likely to dissolve a nonpolar solute. And what that really has to do with is breaking down the interaction between the two molecules and sort of balancing that out with the attraction between the solvent and the solute. So the solvent the attraction to the solvent has to be strong enough to break that interaction between the two solute molecules. Okay, so if I have dipole-dipole interaction between my solute molecules, my solute-solvent interaction has to be strong enough to break that. Okay, and that's how I end up forming a solution, which is probably a little more than you need to know for this particular lab. Okay, so if we just start out from matter, we can have two categories, pure substances or mixtures. A pure substance contains only one type of particle, and this could be either elements, so something you find on the periodic table, like carbon, oxygen, gold, etc., anything you found on the periodic table. Those would be pure substances that are elements. Okay, it could also have compounds. Now this is something that contains only maybe one type of molecule. Okay, so that would be, it can be more complex than an element, but it only contains one type of molecule. So that could be salt, sugar, pure sand, let's say, silicon powder, anything like that would be considered a pure substance, but it would be a compound if it's more complex than just a simple element. And within that, that could be ionic, if we have polar molecules, it could be nonpolar covalent, or it could be polar covalent. Okay, so we have any of those types of interactions. Okay, so what about mixtures? So now a mixture is a type of matter that contains two or more pure substances. So in other words, I have more than one thing mixed together, so that makes it a mixture. And I could either have homogeneous, this is the form of solutions. So I have a mixture that's homogeneous, we could call that a solution, no matter what phase it's in. By the way, this could be liquid phase or aqueous phase, gas phase. So you could even have a solid phase mixture. Okay, so like an alloy. Think about an alloy. Or I could have heterogeneous. And now this is a mixture where, again, I can see the individual parts. Okay, so maybe I mix something like sand together with water, as I said before, and I could pick out the water and the sand. That's the easiest one, I think, to kind of get your brain around. But this could also be, for instance, if I took sand and mixed it with something like carbon powder or something like that. Okay, that would also be a heterogeneous mixtures. So the important thing here is that they have distinctly visible parts. So you can think of a pizza, a fruit salad. I think I use the example sometimes vegetable soup in my classes, where you can see, okay, there's a carrot, there's a green bean, whatever it is. In the homogeneous solution, of course, this is where we can't distinguish the salt water, sweet tea, metal alloys. So as I mentioned, things like brass, copper, brass alloy, and things like that. So if I am all in the same phase, those are homogeneous. If I'm in different phases, they're heterogeneous. Okay, and now under homogeneous, I could have a nonpolar solute and a nonpolar solvent. Okay, I could have an ionic polar solute and a polar solvent. This could be like brine, which is salt water. Okay, brass, which is a mixture of metals. Okay, then I could have a polar covalent solute and a polar solvent. So this would be something like sugar dissolved in water or Kool-Aid. I give the example here. Or HCl, so where I have a strong acid which ionizes, that can be dissolved into water. Okay, then back on the heterogeneous side, just some examples. This could be polar solute and nonpolar solvent, so salt and absolute ethanol. Okay, so ethanol actually has some polarity to it. Or we have a nonpolar solute and a polar solvent. So an example here would be oil and water. Okay, so I hope that wasn't too much to digest there. But that's sort of your flow chart of all the different things you could have. But just remember, like, dissolve, like, and then think about your different interactions that you could have in terms of dipole, or if it's nonpolar or is it polar. Those kind of things are kind of what you need to think about. Okay, so let's dig into what you're actually doing. So for this experiment, we want you to actually take a video recording of yourself performing the steps. And if you don't want to necessarily show yourself, you could just show your hands. That's okay. But you'll attach that along with your report sheet. And so what are we actually doing? So you're going to label some test tubes. Okay, then you're going to add a small amount of salt to test tubes 1 and 4. And by a small amount, it just suggests here enough to fully cover the bottom. Okay, so just a small scoop. Then you're going to add the same amount of sugar to 2 and 5. And using a pipette, you'll transfer enough vegetable oil to do the same thing to 3 and 6. So just cover the bottom. And again, if you don't have vegetable oil, anything like olive oil, peanut oil, sesame oil, anything like that would work here. So basically, you're going to take the 6 test tubes. You're going to put salt in 2 of them, sugar in 2 of them, and oil in 2 of them. Okay, then using a different transfer pipette, add 2 to 3 squirts of isopropyl alcohol, 1, 2, and 3. And then using a third pipette, you're going to put water. Okay, so it wants you to closely examine the 6 test tubes and determine the solubility of each mixture. So how are you going to decide if something's soluble? Well, does it dissolve or not? If it doesn't dissolve, okay, then it's not soluble. If it does dissolve, then it's soluble, of course. Okay. So then you'll record the results in the solutions and solubility table on your report sheet. As far as waste disposal, everything can go down the sink with just lots of water, and then just allow them to air dry. Okay. Let's take a look at your report sheet and see if there's anything we should talk about. I think that pretty much covers it in terms of what we need to talk about. And in terms of the video, you can either, you could email it to me, you can include a YouTube link in your report sheet, or you could also upload it as a second file to Blackboard. Whichever one of those ways is most convenient for you, feel free to handle it that way. Okay, if you have any questions, please feel free to email me, stop by my office hours, and I'll help you out.